Where were they? They took them through. There it is. I was looking for an hour and a half. Damn, he's taking that deal, bro.
Yes, 11. Okay, you ready? First thing, who have not signed the release form for the field trip yet? Field trip release form, how many? One. Who else? Field trip release form. Just one. Who have not signed the field trip release form yet? Just one. Can you get it from TA? Okay. Alright, we will have the release form for you. We will talk about homework a little bit. It is due tomorrow night. Okay. And then 6 hours later we will have a field trip. Okay. Field trip. For the field trip you have to bring your safety glass. Do they need a hard hat? No hard hat. No hard hat? Okay, no hard hat. And if it is cold, bring your jacket too, okay? If it is cold. We will talk a little bit about homework, and then we will try to finish the gas liquid separation, and then go over liquid separation. You ready? Okay. Some of you asked me the question about this part. Question number 2. Gas flow rate at standard condition 14.7 psig. Should it be psia? Yes, it should. It is my typo. If you did with psig, it's fine. Okay, because it's my mistake. If you did it with psia, it is also fine. Okay, because the standard condition is not 14.7 psig. So if you did do it, it's not fine. Okay, if you do it with psia or psig, it is fine because it is my typo. All right, that's the typo here.
So that was meant to be psia.
That was meant to be psia. Okay, next step. 15 Celsius is 59 Fahrenheit. Okay, they are not identical. Okay, that one is 60F, this one is actually 59F. Okay, and that one is 14.6956 psia, and that one is 14.7, very close. So you should get something that very close. Very close means maybe 0.1% different. It should have a little bit of difference. So the procedure to convert from one to another, one standard condition to another standard condition should be correct. Okay. So try to do it. If your answer is correct, it should be almost the same. Okay. When we report one flow rate at one standard condition and another standard condition, it should be almost the same. Okay. More on the homework. This one we asked about the actual velocity or something. We have the actual velocity of 30 feet per second, and from that you want to get the standard flow rate. Okay, everyone did that without any problem? Many of you come to see me, so let me explain here so I don't have to open the door for you to come again. That's my question. Okay, this one is number 2. I think it's number 2. Okay. You may recall the equation that have V equal to 60 something. Do you? Yeah. Okay. V equal to 60 multiplied by Q sub G T Z D square P. and you see the derivation, right? So that Q sub G is standard gas flow rate. It has S, okay, MMSCFD, that is flow rate at million standard cubic foot per day. Okay, that is Q. That T is the temperature that corresponding to the actual temperature, the temperature in the pipe. Okay, that compressibility factor Z is the compressibility factor at the actual temperature and pressure, not standard pressure temperature. Okay, so that P is not standard pressure, it's the actual pressure in the pipe, and that velocity is the actual velocity in the pipe. So this means that if you have actual velocity of 30, put 30 in place of V, right? And put the temperature and pressure of the one that is inside the pipe, right? Then get compressibility factor from the chart. Then you can calculate MMSCFD from this equation. Good? Not good. It's easy, right?
Does
Yes.
that give you Q actual, not Q standard?
Did I give you Q actual? I don't think so. Let's take a look. I give pipe diameter. D, right? Diameter. Make sure that you use the right unit. I give you actual velocity. That is V. Okay. I give you composition of the gas so you can get the
I understand all that.
Gamma.
My question is in reference to the Q. Is that Q actual or Q standard in the formula?
what do you think?
I think it's Q actual. Since you get a V.
What about MMS? S? What is that S?
Oh, so it's standard?
Yeah, I think so. Okay, it's good?
Sorry.
Everyone good? It's okay. I just have to emphasize that it's have S, okay?
That was so easy, it was hard.
Yeah. Okay.
Yeah, it's easy. It's hard until I tell you how to do it, right? That's what it is. Okay, we will try to cover all the, do the homework, okay? The deadline, I don't change it. Sadly, we don't have homework today because we have field trip. Tuesday, next time, bring the calculator in case that we have a quiz, okay? Good. We may not have a quiz next Tuesday. Bring your calculator when you come to class. So this one is gas liquid separation. So last time we talked about C sub D, right? Drag coefficient. Okay, drag coefficient, and we talk about the terminal velocity, V sub T, and the derivation of it. Did I? Ernest, when did we stop?
I wrote it down.
Oh, you wrote it down? Chris? Terminal velocity, right? Okay, so do you memorize the equation for the terminal velocity? Like Vt equal to 1.787 something? Do you memorize that for the test? No, you don't. Okay. I may give you Vt equal to some constant multiplied by delta St d square over mu, and I may give you the starting equation. Okay. Starting equation, I may give you that one and that one. From those two, you should be able to tell me how to get that. Okay. Very easy if it is open book, because it is already in the lecture, you just have to print it. So if it is open book, I don't think we should have that question. Okay, we talk about the drag coefficient, right? So for this part, you see C sub D equal to 24 over Reynolds number 3 divided by square root Reynolds number plus 0.34. Who's strong? Whose last name is strong? Okay. What's your first name? Adam, yes. So that formula, is that for laminar flow or non-laminar flow? Cannot use for laminar flow, right? Okay, so you got it right. So if it is Creeping flow, Reynolds number less than 1 for flow past a sphere. It's just 24 over Reynolds number, right? So we have the derivation. Now we have this chart. And I have already told you that we didn't go over that yet, did we? So when we have the formula like this, what you may have to do is do the iteration, okay? Iteration is for unknown and sure to do it. Actually, we use a chart, okay? This whole thing, you study the difficult way to doing it first, and then later you will see the chart, and it is more reliable. But without a chart, what they do is, you see this C sub D? The iteration process, they assume C sub D to be 0.34. Put it over here, the drag coefficient, get velocity. From velocity, calculate Reynolds number. From Reynolds number, put it back to get C sub D. And repeat the process. The example of the iteration will be given at the last slide of this lecture, okay? Go over it later. Let's do something that is not quite fun. This one, you see Reynolds number equal to 7741 multiplied by something, something, something. See this? Do you know how to get 7741? Yes, of course, if I give you the conversion factor, right? So, you should be able to do it. It is expected to be in the exam, very likely, or maybe in the quiz on this coming Tuesday. How about that? So, what you have to know is, not many. You have to know just, okay, 1 feet is 0.3048 meter, just that. And 12 inch equal to 1 foot. And 1 million micrometer is 1 meter. Put all those numbers in, you get this. Very easy, right? Oh, I don't know if it's easy or not. I will know on Tuesday whether it is easy or not. Yeah. Bring your calculator, okay? It may or may not have a quiz. Okay? Okay, look at the Reynolds number in the field unit. Okay, Reynolds number in the field unit. You see this one? We have rho VD over mu. Okay, and there's some conversion factor. What you need to know, actually you don't need to know if it is a quiz or if it is an exam. I will tell you. I will tell you that 2.2046 pound equal to 1 kilogram. I will tell you 0.3048 meter equal to 1 feet. And then I'm done. Okay? Then I'm done. Then you should be able to tell, oh, I may tell you this part too. I may tell you viscosity from pound per foot second equal to 0.67 something over 1000 of CP thing. Just this. And then you should get this. It takes about 15 minutes to review it, and I don't know if you will review it or not. So we should have quiz on this part, right? Maybe just these two is enough for 15 minutes. Okay. Good. Droplet size theory. Miss extractor get 110 to 100. So by now, I think this number you should memorize because we talk about it too many times. Okay. Miss extractor remove 10 to 100. The rest, just for information, okay? Gas scrubber scrub something that is 500 micron plus. It depends on how they design the gas scrubber for the compressor. For vent and flare, do we have mist extractor? Maybe. Okay. For vent, normally we don't put any mist extractor for vent. Okay, because if the mist extractor get plugged, we cannot vent it, right? Okay. So vent, we don't have mist extractor. Flare system, in the textbook, Arnold Stewart said we typically don't have any mist extractor on the flare system. But for offshore, sometimes they have mist extractor plus safety relief valve. Okay? Because if there is oil droplet go to the flare, and if that oil droplet is big enough, what happens? When it go to the flare, it gets burned, right? Guess what? That burning oil will fall down, and they call, what do they call? Burning liquid droplet fall down before it is consumed. So you have like a fireball falling down to the deck. It's not good, right? So that happens because the liquid droplet is too big. and it won't be consumed before it reaches the ground. That could be some hazard. So sometimes they put the mist extractor in and also put the safety relief valve in case that mist extractor get plugged, so everything come out from the relief valve. Okay, retention time concept. Retention time most of the time used for liquid phase. Okay, so retention time is the average time of a molecule of that liquid to retain in the vessel. Basically, when you use a chart that later we show, you just use this retention time. For gas liquid separation, we should use 30 seconds to 3 minutes. Okay, do we use 30 seconds or 3 minutes? It is depending upon API gravity. Okay, and you will see that table later. Reentrainment. We talked about that a little bit already, that if the flow rate is too fast, gas flow rate is too fast, gas can make the droplet condense from or coalesce from the mist extractor to be reentrained into the gas stream, right? So that's not good. And the rule of thumb is this: the shape of the separator actually matter. If the shape, the slenderness ratio is more than 5 of a half full separator is not good. What is slenderness ratio? It's the length divided by the diameter. That number will be, the formula will be given later, but it's the length divided by diameter. Okay. For high pressure and high viscosity, there's a more chance for reentrainment. Just for your information, not in the test, but just come to the lecture is enough. So horizontal separator, half full, that is a formula. Do we actually use it? Not really. Do you use it in the homework? No, I don't think so. Okay, and later I will show you why do we study it at all. So this is a horizontal separator, half full, 100 plus micron removal. So diameter of the vessel multiplied by the effective length equal to some formula. Okay, take a look at the right hand side. Okay, you will see that the dimension of the separator is dependent upon temperature, compressibility factor, pressure, flow rate, drag coefficient, diameter of the droplet, that is d sub m. So this means for someone to be able to tell how big should be the separator, option 1, they have to know what is the gas molecular weight. From the gas molecular weight, you can get gamma, right, the specific gravity, and can open the chart to get the compressibility factor. So we get this one. And they have to know the flow rate, know the temperature, know the pressure, calculate drag coefficient. If it is turbulent flow, they have to reiterate. So how about velocity? How do they get velocity for calculate drag coefficient? The velocity has to be the actual velocity inside the separator. So actual velocity is the volumetric flow rate divided by cross-section area. Do we actually do that? No, probably not. You use a chart, okay? But I want you to see the equation so that you understand the information that is in the chart should be dependent upon what parameter, okay? Let's take a look how they derive it. Velocity equal to flow rate divided by cross-section area. Cross-section area for the half full is a half of the circle, right? Half and pi d squared over 4 is the area of circle, correct? So that is the flow area of the gas phase, okay? Cross-section area of the gas phase in the horizontal separator. So that is to calculate velocity of gas in the horizontal separator. Okay, look at this one. Q actual cubic foot per second to Q SCFD. You can actually use this one for the exam or homework too. If you have the standard condition flow rate, how do we convert that into actual flow rate? Use this. Basically, it's a PV equal to nRT. Okay, so we have The first couple terms is to get from million standard cubic foot to be cubic foot per second. That's the first 4 term. Okay. The last 2 is from this part. If you have PV equal to Z nRT, Z at the standard condition is 1, right? You may have the ratio of V1 over V reference equal to ZT over P multiplied by the reciprocal of that term. So it's a relationship between volume after it expands and volume before it expands. When I say it expands, it at the standard condition or V reference, V ref over there. Move this over there, so these 2 terms is that kind of 2 terms, okay? So basically it's a conversion of gas at the standard condition to be in the actual condition. So what they did is get the velocity. After getting the velocity, calculate the settling time. Time equal to length divided by velocity. So after get settling time, calculate the time that we actually allow fluid to have. So retention time, if I recall, where's the sign-up sheet? Everyone sign it?
Still going.
Not yet? Okay. Once you have it, give it back to me. Okay, so I can't call your name. But I remember a couple of you. Jim Lee, what is your retention time? What's the definition of retention time? Which page?
Time,
Pardon me?
the gas needs to separate from liquid.
Time?
The time the gas needs to separate from liquid.
The gas need to separate from liquid. Let's check. What was the answer? Red? Red? What is your definition for retention time?
Whatever it is in the slide.
Whatever it is. What about you? Oh, come on.
How long is it?
Oh, is that the retention time?
No.
Retention time. Time that required for it to separate. What about you? You have what's your Stan? What's your definition for retention time?
The amount of time that fluid stays spent in the separator.
Correct. The amount of time that the fluid will spend in the separator, that is how much time that is retained in the separator, that's retention time, right? The time that is spent in the separator may not be enough for it to separate or may be enough for it to separate. Everyone sign the sign-up sheet? Okay. Place mark. I think they have university excuse for something. K. Posty, Stephen, Louis, and Marty, Peyton, Jacob. Oh, several people go to that meeting. Okay, it's okay. So retention time, it is not the time that is taken for it to separate. It's the amount of time that gas or a liquid, retention time of liquid is the amount of time that liquid spend in the separator. Okay, on average. All right. When we have that retention time, so settling time, this part is about the velocity. That velocity is the velocity in the horizontal direction, right? So length of the separator, effective length in the separator divided by the velocity give us the time that is spent to travel horizontally, correct? The amount of time that the particle or liquid phase stay inside. Okay. Look at this one. D over 2 divided by V sub t. V sub t is the terminal velocity. Terminal velocity has the direction of downward, right? And that D over 2 is the length from the top to the half of the bottom. So it is the time required for the droplet to fall down. The first term is the time that the liquid particle or liquid droplet spend to travel horizontally. The second term is the time for the droplet to fall down. make these two terms equal to each other. So saying that we give a certain flow rate so that the time required for it to fall down is the time that is spent inside the separator. This way it's separate, right? So the time that is spent inside equal to the time that is required for the droplet to fall down. Then calculate T sub G. Okay? Rearrange it. So we put Vt equal to 0.0119. So that's the terminal velocity equation that we got already, or the one that you will derive on this Tuesday, if you have a quiz. Okay, right? That 0.0119. So then you get this equation. Rearrange it again, you get that thing. Okay, for horizontal separator, half full. If it is 1/3 full, you cannot use this equation. It is not the same. This is for half full. Okay. So we need to know the assumption behind this kind of calculation. The assumption is the droplet reach the terminal velocity right away. In reality, it's not like that, right? If you have a droplet, it takes a certain amount of time to accelerate until it reaches the terminal velocity, correct? So if I do this, it takes a while until it reaches the constant velocity. So it doesn't reach the terminal velocity right away. And look at this part. Do we have laminar flow? Maybe not. Maybe we have, we don't know. So we put C sub D over there. If it is not laminar flow, we may have to do iteration. Oh, that will be too difficult than using the chart.
Question.
Yes.
Didn't you make a distinction between creep flow and you had to...
Creep flow is Reynolds number less than 1 for flow past the sphere shape.
So can we still categorize it into laminar and turbulent flow?
Creep flow is laminar flow. Yes, we can say laminar and turbulent. Creep flow is certainly laminar flow. Okay, this.
Question.
Yes.
How do you measure your QE?
QG. If we look at this term, actual velocity is the actual volumetric flow rate divided by A sub G, right? But we don't know the actual volumetric flow rate, so we find the way to convert from Q sub G, which is the volumetric flow rate at the standard condition, to be actual volumetric flow rate.
Yeah, but how do you get QG?
QG has to be given. So let's say we do the production and we know that from reservoir calculation or something, we estimate, okay, this field will give us this well will give me 1 million standard cubic foot, another well give 1 million. I have 10 well, I should have 10 million standard cubic foot for this vessel. So QG is the given number based on the estimation of how much should come in. If we know that it will come in at 10 standard cubic foot or 10 million standard cubic foot, so we may multiply by 1.2, 1.5 or something and size the separator based on that. Make sense to you? So if we have more volume coming in, we use a bigger separator. Make sense? That is indicated by this formula. So more volume coming in, diameter or the multiplication between diameter and length has to be more. Okay? Effective length is the actual length that separation happened, which should not include the length that occupied by oil bucket, water bucket or something. Okay? How do we know the actual length of effective length? We don't know, we can estimate it. Okay? But the best way to do is to use the chart provided by the manufacturer. And this looks very nice. You haven't seen it yet. Okay. Liquid capacity part. So for the liquid capacity, we size it based on the desired retention time, T sub R. How much retention time that we think we should have. Okay, put the number in, we get D squared multiplied by L effective. The derivation is the same idea. So same idea means time equal to volume divided by Q. So that time is the amount of time that liquid will spend inside the separator, right? So the time that liquid will stay in the separator is volume divided by flow rate. And flow rate is the unit has to be consistent. The rest is just the unit conversion to allow you to put in barrel per day instead of cubic foot per second. This is not on the quiz on Tuesday, if we have the quiz on Tuesday. Okay, so then we have the time that is spent in the separator equal to 42 multiplied by something over here, right? So that TR, we should set it equal to the retention time. Then we have this formula, just that. So the time equal to volume divided by flow rate. And that amount of time is the time that we will specify by ourselves. We call it retention time. We hope that the time that is spent inside will match the recommended retention time. Then we can know how much this separator can hold the liquid capacity. So if I don't actually know the size. So if I say, okay, retention time equal to 1 minute, I put number 1 over there. I put QL in barrel per day divided by 0.7, then I get D square multiplied by length. I don't get diameter, I don't get length. It's not the final answer yet. Okay? It is not. So it's kind of more difficult to use. Okay, seam to seam length and slenderness ratio. This one is the quick guess for us. When we have a separator, when we say, okay, separator is 36 inches by 10 feet. That 10 feet is the seam to seam length. It's not the effective length that the liquid droplet or gas will see. Because in the separator, there's something in between, right? You can have oil bucket, water bucket or something, occupy some length. You can have mist extractor. Mist extractor stay on the frame. The frame also occupies some space, right? So the actual length or the effective length that the liquid see is not the same as seam to seam length. So this is one way for a quick guess, okay? And D is in inch. L sub effective length has to be in foot, okay? Foot or feet. Okay, seam to seam length should consider the space required in the mist extractor and inlet diverter, because inlet diverter occupies some space, right? Okay. Slenderness ratio is just the recommendation between the length over diameter ratio. The length over diameter ratio should be between 3 and 4. What is actually happened is we cannot really say, hey, I want the diameter of 3 feet by 11.2156 meter or something. We cannot. They sell at a certain size. And when they make it, it is already at the recommended slenderness ratio. So we don't actually have to worry about this. They don't sell every size. They sell only the size that actually work. Okay? Make sense to you? We just have to use that chart. But think about this. What about the first person who built a separator? How do they know? They didn't buy from someone else, right? They built it, so they probably have to know this. Okay. This is the calculation procedure if you use the formula. In the homework, I haven't made the homework yet, but I try to not have this part. But what you can do is get the factor of D multiplied by effective length from gas capacity equation. Okay. Look at the right hand side. The right hand side can be calculated if you know the flow rate, fluid property, right? You can calculate the right hand side. Then you get the length multiplied by diameter. Just that, not the length or diameter separately. You get the combination of both. Then you do another equation for liquid. Okay, and T sub R use the recommended retention time. You remember, you see the word recommended retention time. How can one recommend anything? It's come from empirical correlation, right? Or the test, experimental test. So that's T sub R. And LSS, seam to seam length, get seam to seam length from both equations. So if you have L multiplied by D and you have D square multiplied by L. So the second one divided by the first one, you get D, right? The second one you have D square multiplied by L. The first one you have just D multiplied by L. So second one divided by the first one, you get diameter. Correct? Once you know diameter, then you can get length. Okay? Then we have to select the proper size of the slenderness ratio between 3 and 4. Okay? Don't go over 5. That's the recommended value from Arnold Stewart. Okay. The one that you have seen is for horizontal separator. So that formula for TQ over 0.7, that's horizontal half full. That 420, that horizontal half full. Okay. They also make the equation for vertical. What I want you to know is not the final form, but try to see how do they derive it. What kind of first equation do they use? So they use the same thing, okay? Gas velocity equal to flow rate divided by area. But look at this one carefully. The area for the vertical separator is pi d squared over 4. For the horizontal one is pi d squared over 4 multiplied by 0.5. Because another half occupied by liquid, okay? But for vertical separator, the whole cross-section area is the flow area. Make sense to you? So we multiply by 0.5 because in the horizontal one is another half occupied by liquid. But for vertical one, it's not. Everything is for gas. So that one is the conversion factor to change from standard cubic foot to actual cubic foot. Yes. And then put everything inside. Oh, look at this one. V sub g equal to 60 multiplied by Tz Qg over Pd squared. Isn't that look very familiar? The one that you use in homework, right? Convert the actual or standard cubic foot to actual velocity. Okay? And you get terminal velocity. This time you match the retention time and the time that we give for it to flow. Okay? The retention time will be length, which is the vertical length, right? That's the length. Divided by velocity. That velocity will come from 60 Tz Qg over Pd squared. That's the terminal velocity. So length divided by velocity give us the amount of time that droplet will spend inside. Okay? And if we use that length divided by terminal velocity, it will give the amount of time that is required. Okay, the first one is the time that is spent inside. The second one is the time that is required. So basically you match Vt and Vg, rearrange it, and then you get d squared equal to something, something, something. Okay, that's for vertical. Formula for the vertical one. Isn't it look very similar? So for horizontal one, we get 420. Okay, dl equal to 420. And this one is not L, it's D squared. That's the difference. Okay, this time you get D squared. So this means if you know the right hand side, you can calculate diameter of the separator right away. Oh, very great. How do we get CD? Do we iterate it? Probably yes, because it is not going to be the creeping flow. Okay? You may have to do some kind of iteration. So Reynolds number is the Reynolds number of the flow. So this rho Vd over mu, rho will be the rho of the flow. The viscosity will be viscosity of the flow. Okay, this is for the clarification that may make you confused last time. So Reynolds number is the dimensionless number for the flow. And we have flow around the sphere, right? So rho and mu has to be the one of the flow or the fluid, not the solid one. We treat the droplet as a solid particle, okay, in the hydrodynamic calculation. For this time, we instead of 0.7, we get 0.12. Look at this. Just change 0.7 to 0.12, and the left side, d square h. Earlier we get d square L. Look very similar, right? D square h and d square L. So that is the liquid capacity for the vertical separator. Okay, liquid capacity. So this means H is the height of liquid volume. So this equation tells me that the separator will handle less flow rate if we have almost liquid full, right? We don't have enough time for gas to separate or something. So the amount of liquid, if we have more height, it can handle more liquid. Okay. Of course, if we have more height, it should handle somewhat less gas, isn't it? We kind of have less length. Oh, probably not. It doesn't have length dimension over here. Okay, look at this one. The amount that the separator can handle for liquid is depending upon the liquid height in the separator or the set point. Okay, if we have it taller or lower, it impacts the amount that the separator can handle. But you have to keep in mind that when we actually buy the separator, the set point is already set, and they already set the dumbbell or something. So they just give you the chart to use, and everything in this equation already included in that chart. You want to see the chart yet? You just go up, go left, and done. Just that. But let's take a look at some more complicated thing first. So before you use the chart. The idea of getting that is the same, but the number instead of 0.7, it changed to 0.12 because this time QL is BPD, barrel per day. Okay, barrel per day. Marshall, how many people do we get? How many students do we get in this room? Can you check if it's match the number in the sign-up sheet? Alright, so that's the conversion factor. We try to change from BPD to Q, and that Q is cubic foot. So because of different units, then we have a little bit different formula. Okay. Okay, for the vertical separator, how do we change or convert from seam to seam length to the actual length that fluid see, or the effective length? So they said, okay, seam to seam is depending on height plus 72 divided by something. So actually, it is here. Okay, look at this part. We have liquid height. This part is H. Okay, and we have 2 feet minimum below the inlet. Okay, that part has to be 2 feet, and we have another 4 inch over here, 6 inch over here, and you can have the length from diameter plus 6 inch or diameter plus 42 inch. So this seam to seam length is the relationship between the liquid height and the actual thing in the separator. Okay, when you actually size the separator, you don't check any of this. Believe me, you don't need to check any of this. There's a recommendation for the relationship between the height and the seam to seam length. Okay, and the manufacturer already built it according to this recommendation. Okay, make sense? They have to build it right, so they should know this. So the relationship between the height and the length of the separator should be set at a certain recommendation. They already do this, so liquid level will be a certain length below the inlet or something. So this relationship already fulfilled, certified by the manufacturer. What's that? It looks like this, okay? When you buy it, or when you actually size the separator, you have to tell, do I do 24 inch by 5 feet? I use 24 inch by 7.5, or 24 by 10, or 30 by 5. You cannot select 30 by 5.5, right? It's not something in between. And you can calculate the slenderness ratio already. And when you buy the separator, not quite likely that they will tell, oh, what do you want the liquid level to be set at? It's set already to be consistent to the this kind of calculation, this detailed calculation. Okay, so it is nice for you to be aware that there's certain relationship that liquid height has to be related to the total length. Okay, and that is a relationship here. Okay, how much is the retention time? This one you need to know. Okay, this one is important when you actually size it. So if you don't know anything, you can say, okay, gas liquid, this oil kind of thin, let's do 1 minute. Is that enough? Yes, for 35 plus anti-gravity. Okay. If the oil is somewhat denser and more viscous, anti-gravity of 30, let's use 2. 25, use 3. 20 or less, use 4. If you have foam, multiply by 2 to 4. Okay. If you have carbon dioxide, use minimum of 5 minutes retention time. So you may recall, if you have carbon dioxide, most of the time we will certainly have foam, right? So retention time, or the time that liquid should retain or stay inside the separator should go up. So it's have enough time for the separation. So do I give you this table in the exam? I haven't made it yet. Probably. Okay. You don't have to print anything. It's open book. Normally last year we don't give it, and many people complain, so we change. Oh, everything here come from Arnold Stewart book, the yellow, orange book, and the graph thing. This from Silva's textbook.
But is this in a different slide set than what we have?
It's a new update.
It's a little bit updated. Added more. You don't have to reprint the whole thing. You just print more stuff that is added in the back. Sorry about that. Liquid phase retention time calculation. Oh, this equation you have to pay attention to. Okay, it's the one that you actually use. The one fancy, look very big, that 50-40 thing, you don't actually use this. It's too complicated and it is not as accurate as using the chart. But how do you use the chart? You need this formula. Okay. Now, open your eyes. For those who sleep, open your eyes. No one sleep, I know that, you're senior. Okay. You have to do W equal to a conversion factor multiplied by volume. This V is not velocity, it's volume. Sorry for the confusion, but I put in the parentheses that is BBL, barrel, okay, per minute. How do we use it? Okay, look at this one. When we have flow rate, barrel per day, we put it on the left side, right? Or typically we don't know W. We know how many barrel of the settling volume do we have in the separator. So when we open the table, we read settling volume barrel. Okay, this one, for example, is the settling volume for horizontal separator high pressure. High pressure means this thing is rated for 2000 or 230 psi to 2000, but basically you open the right table. You go to the table and you find out. If I use 30 inches by 5 feet, so my retention time, my settling volume is 139. Settling volume is the actual volume that liquid see. Okay? Already include the impact of any wave eliminator, any foam, anything inside vortex, breaker or anything, because it's from the experiment, it's from the manufacturer. So read the settling volume, that is BBL, right? That settling volume will be V. Go back to the retention time. Retention time. Okay, API gravity of 2. Okay, API gravity of 30, we use 2 minutes. Go back to the formula. That point something, put it there, retention time, put it there, multiply by that, so that W will be barrel per day that separator can handle. Good? Okay. So how do we get 1,440? Okay, look at this. Volumetric flow rate in the unit of barrel per minute equal to volume in barrel divided by time, which is in minute. Make sense?